Before we dive in any deeper in the manipulation of signal space, I'd like to give you just some examples. So I'm going to look at some quaternary examples, that means 4 symbols, and look at manipulations and what the interpretations and effects are in signal space. And then when we start speaking more generally, I hope that these examples from 4 symbols will help you understand and interpret what we're going to see next. So symbols are the discrete collection of values that will be transmitted. So they can be represented in signal space, the symbols themselves. And of course, the received signal is the transmitted symbol plus noise. So all of these things, symbols, received signals, noise, they all can be represented as vectors. And again, we choose an orthonormal basis. The collection of basis vectors we call CI. And for example, if we're going to look at the signal that was either transmitted, one of the symbols, or later we could look at the received signal, it's going to be a vector in the signal space with up to n coordinates. And each one of the coordinates we find by taking the waveform for that symbol, or the received signal, and doing the inner product one by one with each one of the basis vectors. And of course, the modulus squared of the vector, or the 2 norm squared, is the signal energy, and that just comes from this definition. So that's, remember, a little recall on signal space. So as I mentioned, I was going to look at quaternary and also binary. So here are signal space representations for 5 different modulation formats. And again, I'm going to take you through how we can determine the correct coordinates in signal space for these simple examples. So the first example is what I call antipodal signaling. We've called that antipodal. We also have seen that it could be called binary phase shift keying. So there's one symbol to the right, starting at the origin, go to the right and to the left. And this is actually a one-dimensional signal space, but we're plotting it in 2 dimensions to compare it with some quaternary ones, which are in 2 dimensions. Next we have an orthogonal modulation scheme. We've seen one orthogonal modulation scheme, and that was on-off keying, but we've also discussed another one, which is frequency shift keying. And in this case, I'm going to show you something for binary frequency shift keying. And in this case, in 2 dimensions, we would write this as one vector along the x-axis, the other vector along the y-axis. And because they're along the x and the y-axis, of course, they're at 90 degrees separation. They are orthogonal from one another. The other example we saw of a binary orthogonal modulation was when one of the vectors was at the origin, and in that case it was a one-dimensional space. But here it's actually a 2-dimensional space. So another example now would be QPSK, which is quaternary phase shift keying, which is kind of a mix because we can think of it like antipodal. If we take it, so here are 4 symbols on this 2-dimensional signal space for QPSK. And if we take S2 and S4 here, they're like in opposite directions, right? So they're like antipodal. And if I take S3 and S1, they're like in opposite directions. But if I look at them along different pairs, then they actually look like orthogonal. So like S1 and S2 are orthogonal to each other, S1, S4, etc. So QPSK is kind of some sort of hybrid mix between the example in binary of antipodal and of orthogonal. Now, if I take that QPSK constellation, so QPSK means that each one is represented by a different phase. So they're all at the same distance from the origin. They all are inscribed on a circle. And I could indeed plot that 2 different ways. For instance, if I just take this same 4 points but rotate them, if I rotate them, then I could use this representation. So why would I use in QPSK in signal space this representation versus this representation? And what is the impact of having a rotation of a constellation? So constellation, that's what I mean by the collection of points, the collections of symbols in the signal space. And here I show you a rotation. And then so this is the same modulation format. I've just rotated it within the same signal space. Another way I could have manipulated it was to do a translation. So now I start with this one and I sort of push it to the right. And so instead of having them equidistant from the origin, I put one at the origin, but now they're still, the distances, the geometry is still that they're antipodal and orthogonal. They're the four corners of a square, if you will. So my goal now is to look at the impact of these manipulations in signal space. What happens when we rotate? What happens when we translate? And we'll start with this quaternary example as making it kind of simple. So before we go on to the quaternary, we're going to start again with the binary. Just remind you of what we've already done. We've already done this analysis of antipodal and on-off keying. And if you'll recall, when we did this operation, we were careful to do the normalization so that the average energy per bit, so EB is the average energy per bit, is the same in both cases, so that this distance represents the energy of symbol 1, this distance modulo 2 squared gives you the energy of this symbol. Of course, the symbol at the origin has 0 energy, but this one, this length represents, is associated with the energy of that one. But now if I took the average energy, I take the energy of this one plus the energy of this one, divide by 2 because there's 2 of them, the average energy per bit would be this symbol EB. That's why I chose EB. And I would get the same thing here. If I took 0 plus 2 EB divided by 2, I'd get the average energy per bit is EB. So this is how I am sure that I'm having a good normalization. Now let's see if I did that with BFSK when I showed you this representation in signal space. And indeed, in this case, this length is the same as this length, and this energy is the same as this energy. Just like here, these are equal energy. So in this example, both of these are equal energy examples. So it's a little easier when each bit has the same energy, then the EB is kind of obvious, right? So if this length is square root of each EB, this length is square root of each EB, then the energy total is the same, and that's what's happening, exactly what's happening here. Except here they're 180 degrees out of phase, and here they're 90 degrees out of phase. Now, what's interesting is that I can find the probability of error. We saw for the binary signaling before that the probability of error here is determined by this distance, this separation between symbols. Because ultimately, how much can I tell them apart? Well, depending on how big the noise is, the farther apart they are, the fewer errors I'm going to get. So it's natural that this separation, which we call D, the distance between them, determines the performance. And in fact, for BPSK, we quantified it, and it was D, this D was 2, the square root of EB, and then the probability of error we found was a Q function of the square root of 2 times EB over N0. Now, let's look here at BFSK. We haven't actually done the analysis for BFSK before, but what I'm going to show you now is that because we know signal space, we can cut to the chase and get directly to what is the probability of error for FSK. And that is because it's determined by this distance between these two symbols. So as long as I can find out what D is, then I know the probability of error, because it's really the same situation as here. It's a different mapping, so I'm going to have a different distance, but the development of the distance, the performance based on the distance is the same in the two cases. So I saved myself some effort. So first thing I notice is that when I calculate the D here, just a little geometry with the Pythagorean theorem, I find that the D is equal to the square root of 2EB. So that means when I put it into this equation with the new D, I get the square root of EB over N0. So this tells me that this distance, of course, I know this distance is smaller than this distance. This is 2 times the square root of EB. This is 1.4 times the square root of EB. So BFSK is less performing than BPSK. It is less, as bit error rate is higher. What's interesting is this is the same D that I found for on-off keying. So the on-off keying performance and the FSK performance is the same. They're both orthogonal. They're both orthogonal formats, both orthogonal modulation formats, and it's this characteristics that determine the fact that their performance is actually identical in terms of bit error rate versus signal-to-noise ratio. So I have this definition of minimum distance that I presented, and this is going to be for an expansion to not just binary signals, but now I'm going to apply it to quaternary when I have 4 symbols so that I can apply it to the other example I showed you. But of course, this is an equation, definition, an equation that I can apply to any size constellation. So not just quaternary constellations, not just constellations that are a collection of 4 symbols, but really any size collection. So I'm going to make this definition. Definition is that the minimal distance is I take every 2 pairs. So here is index I, index K, any I and K, I look at that distance between them, and I look for whichever one's the smallest one. So I have 100 points in my constellation, fine. I take each pair, and each pair I calculate how far apart they are. And then all of those pairs, I examine them, and I look for the distance which is the smallest distance. Which 2 symbols are the closest to one another? That is the definition of the minimum distance. So the minimum, of course, if I equals K, then I'm going to get 0. I don't want that. So the minimum over I not equal to K. And I call that my minimum distance. What's really going to be interesting for us, too, is to have a second definition of minimum distance, which is simply a different normalization. So in this case, I'm going to get a dmin, and I will, of course, when I use signal space, these coordinates for these 2 vectors are going to be expressed in terms of the average energy per bit or the average energy per symbol. I can use one or the other. And so it's going to be some function of the average energy per bit. So what I'd like to do is define a second version of this minimum distance. So one is an uppercase d, the other one is a lowercase d. The lowercase d is a normalization where I take out this dependence on the energy per bit, average energy per bit. So specifically it's day min, when the d is uppercase, divided by the square root of 2EB. And the square root of 2EB is related to a particular performance that I would like to compare it to. And so that'll come out a little later. But the important thing is it's normalized with respect to EB. So our intuition, of course, in signal space, why do we use signal space? Intuition is so great. Closer the signals are, the more errors I'm going to have. So this idea of the minimal distance is going to tell me how vulnerable the constellation is into errors, especially as I compare one constellation with another constellation. So closer signals, more errors. Again, I could do it in terms of average energy per bit or average energy per symbol, since I want to make sure that this applies to larger constellations as well. Let's put it in terms of average energy per symbol. And we have the definition here is if I have M symbols in my constellation, the 2 norm here, the modulus squared, I will sum over all M symbols, the energy of each one, of course, divide by 1 over M. That gives me the average energy per symbol. If I want to get energy per bit, if I want to use this normalization, of course, I could either leave capital D min in terms of the average energy per symbol, or if I use this relationship that will let me go from average energy per symbol to average energy per bit, I could leave this in terms of average energy per bit, or I could, after I put this in energy per bit, I could normalize it to get the smaller d min. So M is the number of symbols in the constellation. In binary, M is equal to 2, quaternary, M is equal to 4, etc. And log 2M then is equal to the number of bits per symbol. Oops, symbol. Sorry. So the m equal 2, of course there's 1 bit per symbol because a symbol is a bit. M equal 4, well if m equal 4, then for symbol 1, symbol 2, symbol 3, symbol 4, I could have this correspondence between bits and symbols. And because there are 4, there are 2 bits per symbol. And of course, as my constellation is larger, there are more bits per symbol. So if I want to get the average energy per bit, I just take the average energy per symbol and I divide by the number of bits per symbol. And that gives me the average energy per bit, which is why I have this equation. So now I'm going to return to the examples, and you'll see that this diagram was in Sklar, and he wasn't quite as rigorous as I would have liked in labeling these spaces. And so I'm going to take you through it and make sure that together we get the right labeling in terms of EB, the average energy per bit. So we start with the simple example, this binary case, and with this labeling, let's see if it's true. So the first thing that I do is I say, what is the average, what is the energy for symbol 1? So symbol 1, I take the length, which is the square root of EB, and I square it. That gives me EB, that's the energy. I do the same thing for symbol 2, I get the same result, EB. And that's because by definition in antipodal, S1 is just equal to minus S2, so of course their modulus squared is the same. So now if I want to look at the average energy, that would be 1/2 of this one plus this one, that gives me EB. So that's the average energy per bit. So everything's cool. So I just validated that these coordinates do give me that the average energy per bit, 1/2 of the energy of S1 plus 1/2 of the energy of S2, that gives me EB. And so EB does in fact represent the average energy per bit, and so this result is true, that I can use this d min, and this d min I can put into my probability of error equation. Now let's go on to the second case, which is BFSK, and of course again if I look at the length of this vector squared, the length of this vector squared, both of them gives me EB, so of course the average energy per bit is EB. So these are the good coordinates. Then I say, I use the Pythagorean theorem, and I say, well, what is the separation of these two? And that gives me the square root of 2 EB, the d min, which I can now use in my equation for the performance. Now let's get into QPSK. Let's take, well, first of all, PSK, phase shift keying, is by definition equal energy, that all of the symbols are arranged around the unit circle. Unit circle is not unit, it's just whatever the energy is, that's what it's normalized to be. So for instance, here where I have put here the square root of EB for my coordinates, x and y, and these are the coordinates then of S2, for example, would be square root of EB, square root of EB would be the two coordinates for S2. So I can take those coordinates. So let's say for this version of QPSK, the coordinates are all plus or minus the square root of EB and plus or minus the square root of EB, depending which one they are, right? Plus, plus, minus, plus, etc., or minus, minus, etc. So when I'm taking the energy of any one of these, the energy of any one of them is, of course, going to be plus or minus the square root of EB squared plus or minus the square root of EB squared, and that's going to give me 2 EB. So it's true for no matter which one of these I get. So now if I want to say what is the average energy, and I put EMOY, but let's say AVG, the average, that would be 1/4, and then I would have 2 EB plus 2 EB plus 2 EB plus 2 EB, right? It's pretty clear. And then this is going to give me 2 EB. So the average energy per bit now is 2 EB. So this is the average energy per symbol. So this is per symbol. So in another notation I might use is to call this ES as opposed to EB. Now I want to get to EB. Well, I know that EB is ES divided by log to m. So it would be 2EB divided by log 2 of 4, which gives me EB. Fine. So the average energy per bit really is EB. So poof, everything is okay with this normalization. So we've checked this one, we've checked this one, we've checked that one, everything's fine. I've got the real normalization. I know what the d min is. Of course, again, I can do the, it's clearly the separation between these two is equal to 2 times the square root of EB. And by symmetry, I can see that that's true for all of these pairs. And I say d min because if I take this distance here, it's going to be greater than 2 the square root of EB, but that's okay. It's not included in my definition. My definition is the closest ones. And these two, these two, these two, and these two, these 4 pairs are all at the same separation, and it's smaller than the 2 other pairs. So what have I shown here? I've shown that EB is indeed the average energy per bit, so that's a good normalization. And then from that EB, I can also look at, in this case, the d min, which is not normalized, or if I divided by 2EB, I'd also get the normalized minimal distance. So BPSK, BFSK, QPSK, I found the good representation on single space, the good normalization, and I have the performance, and the performance is determined by d min. So what do we do next? We look at this QPSK and we look at the rotation and we look at the translation, and we see what is the impact of the coordinates. Do the coordinates change when I rotate? Do I have to change the normalization? What's the impact there? And secondly, what is the performance? Does the performance change in these two situations? And I get that by looking at the minimal distance. So let's go through that now. Let's start with the rotation. In the case of a rotation now, my coordinates are now, the coordinates will be 0 plus and minus the square root of 2e, or the square root plus or minus the square root of 2e, or 0, and I'm leaving the e a little ambiguous now. We're going to see is that the right e or not. And in this case, the reason that we're putting in the square root of 2 will become obvious. But anyway, these are the coordinates. Here's 0, square root of 2e. This is square root of 2e, 0. So we have the coordinates, and we can find then if with these coordinates I take the magnitude squared, take the length squared of any one of these vectors, I'm going to get 2EB. And of course 2EB is what I got previously for the energy. So I know that everything works out nicely. It's the same calculation I did just now, that when all of the energies are equal energies, because again, we can see geographically that even though I've rotated, they're all still an equal distance from the origin. Just like they were here, they still are here. So nothing has really changed. And these are indeed the average energy per bit. So I was a little coy, but really putting the B there makes sense, because if I put the B there, the average energy per bit does come out to be correct. Now, that means, what about the minimum distance? And the minimum distance, again, is determined here. This is closer than this one. Here now, with this normalization, we can see that these two antipodal signals are 2 the square root of 2 EB apart, whereas on the diagonal of the right angle, this separation is 2 times the square root of EB. So this is the d min. It's the same d min that we had found previously. So the same performance. So rotation in the signal space, the takeaway is that rotation does not change the performance of a constellation. So it's really arbitrary. I can show this representation for QPSK, or I can show this representation of QPSK. They're both accurate. They're different basis vectors. That's why there's 2 representations, but they're equivalent. Either they both are well normalized, and when they're well normalized, they tell us that they have the same performance. So therefore, rotation of signal space does not change performance. So let's move on now to translation. And in translation, things get trickier. And we're going to see something funny happening. So first of all, we cannot leave this. If I do the translation here and I want to simply move it over, I would be very tempted to think, well, these two were the square, 2 times the square root of EB apart, so I'm going to keep that, and I'm fine. Then nothing's changed, right? But we're going to go through the effort, and I'm going to assume that this is a good normalization. I'm going to show that in fact it's not a good normalization, that in this case, if we keep these kind of coordinates but just shifted, that we'll actually get an energy per bit which is not equal to EB. So let's just go through it. So now my coordinates are 0, 0. My coordinates are 0, 2, the square root of EB, 2, the square root of EB, and 0, and then finally 2, the square root of EB, 2, the square root of EB, right? So they're no longer equal energy. I can see that. This one's got 0 energy. This one's got more energy than these two, but these two have the same energy. Okay, so I have 4 levels of signal energy that I have to keep track of. So I do the math and I say, what is the average energy per symbol, right? Here is ES. Average energy per symbol is 1/4, and then I take, this has got 0 energy. These two have got 4 EB for energy, and then this one has got 8 EB for energy. So that, I do the math, and that comes out to 4 times EB. But of course, energy per symbol should be equal to 2 EB, but here it's equal to 4 EB. So that means this normalization is incorrect. So I have to change it, and I have to change it in order to get the correct normalization. So this should not be 4 EB, it should be 2 EB, so I'm off by a factor of the square root of 2. So instead of having 2 times EB, that 2 should actually be inside the square root. If I put it inside the square root, then this 4 becomes a 2 and everything is okay. So now I have changed the coordinates. I've put the correct coordinates on, which are the square root of 2 EB and the square root of 2 EB here. So you see that when I do the translation requires a new normalization. And when I do this normalization, I can go back and validate again, and now indeed I get the average energy per symbol is equal to 2 times EB, so EB is indeed the correct normalization. So now I have a correct coordinates, and now I have to go in and look at what is the minimal distance. Again, the minimal distance is going to be this. It's not the antipodal. The antipodal is longer. And then this distance is, of course, very easy to see because the dmin then, in this case, is just the square root of 2 EB. So the square root of 2 EB is, of course, different from the minimal distance here. So before I had done the translation, I had the minimum distance of 2 times the square root of EB, and after I translate it, I've made it worse. I've made it worse because now the dmin is 1.4 times the square root of EB. So although when I look at my graph here, they're no longer on the same scale because, because this distance looks like this distance, but this distance is 2, whereas this one is the square root of 2. But the important thing is to do the calculation correctly, even if our drawing is not necessarily comparing to, not correctly drawn to scale. That it pops out right away that translation can make things worse. Of course, we started with the good one here, and then we translated it and made it worse. So of course, if you translate it, you have to renormalize. Most important takeaway. And then I asked the question, why is this one better than that one? Is there some characteristic of this representation that made this better? Certainly, when I started out defining phase shift keying, I said that they were equidistant from the origin, they were arranged around a circle, but I could have defined it as having arranged around a circle which was translated. Why didn't I do that? Why did I say it was around, centered around the origin? And that is because centered around the origin is actually the most efficient way to organize a constellation. So anytime I translate anywhere around the signal space, it's always the signal space where everything is arranged around the origin, which gives you the best performance, which gives you the largest possible minimal distance when you have the correct normalization. Okay, let's look at this idea about what is the best translation. Let Z here represent an arbitrary translation. The energy per symbol as a function of this translation would be to take whatever the symbol coordinates were that I started with. Of course, each one of the symbols is going to be translated by this amount Z, so it'll be moved, and that will be the new coordinate of the symbol after the translation. And so the energy for this symbol after the translation would be this modulus squared. So for a given translation, I start at any arbitrary point for the symbols, and the best translation, we can do an optimization, and the optimization shows us if we want to have the largest minimal separation, then we should put Z0 at the center of mass. So if I were going to interpret all of these symbols as a different weight on a platter, and I want the platter to balance on one point, Z0 would be this point. So if I want to maximize the d min, I should center this constellation on its center of mass. Okay, that's good. But the other thing I want to do is to make sure that I have been as energy efficient as I can. So of course, if I put it at its center of mass, but I put all of the symbols like really far out, they're very far away from the origin, then of course they're going to use a whole lot of energy. Of course, it will still have the minimal distance, but they're going to have a total energy which is really high. So what I want to do finally in my optimization for the very best translation is to actually put that center of mass at the origin. Because if I put the center of mass at the origin, then I've minimized the average energy per symbol. So I'm very energy efficient. So I want to keep the d min as large as possible. That means center everything at a center of mass. And finally, to minimize the energy, I would put that center of mass at the origin. And that's what we've seen when I started with the center of mass at the origin for BPSK in particular. That gave me the most energy efficient solution and the best performance. So in summary, these were the 5 constellations we looked at. We found the d min in each case. We found that there were 3 with the same performance. For instance, here is BPSK with a given d min. We saw that, QPSK actually has the same d min. So very, very similar performance, perhaps equal performance. And if we rotated it, it was also the case. However, we also saw 2 other ones where FSK, we saw that this orthogonal version was less, did not perform as well as the antipodal one. So orthogonal modulation is less efficient in this binary case. And we also saw that translation could worsen performance. So we started at the optimal. We found out later that that was the optimal because we were centered at the origin, and translating it made it worse.